The objective of this project is to launch a bottle rocket with an egg for the longest flight time possible. Propulsion is achieved by pressurizing a 2-litre bottle with compressed air. This creates a force acting on the water. If we add a nozzle to the bottle, we will accelerate the water downwards. This results in an upward force on the rocket due to Newton's third law of motion. Spreadsheet analysis was done by initially estimating the design parameters of the rocket, such as dry mass, bottle volume, rocket and parachute drag coefficients, as well as parachute area. A rough simulation was created that then determined the thrust of the rocket. C++ code was written to validate this rough simulation. The code calculates the forces on the rocket, such as thrust and drag, and turns them into accelerations. The code then integrates these accelerations to turn them into the velocity and position of the rocket. This is a process called dead reckoning. This code allowed a velocity-altitude graph to be plotted, as well as an acceleration and motor thrust graph. Further iterations of the code allowed optimizations of the rocket to be calculated, such as the optimal water fraction and the optimal parachute size, which accounted for the change in mass as the size was increased. Next, Unity simulations were done to determine the fin size and location so that the rocket remained stable. Virtual wind tunnel simulations were also done in Unity, which helped validate the fin's size and location. It is important for a rocket to remain stable that the center of pressure remains behind the center of mass. This creates a restoring moment when the rocket is knocked off course. A parachute is needed for the rocket so that the rocket remains in flight for longer. The parachute is situated inside the nose cone and will deploy when the nose cone separates from the rocket. This will be done by a process called drag separation, where the body of the rocket is accelerated downwards, away from the nose cone, due to aerodynamic drag. The parachute was chosen to be an octagon as it could be easily manufactured, and because of the C++ code, the size of the parachute was determined to be approximately 1.3 meters squared in area. This translates to an octagon with side lengths of 0.493 meters. The final parachute can be seen here. A more accurate sketch of the rocket was made, and then the entire rocket was modelled on SolidWorks. The bottle, fins, and nose cone were made and then attached to create the rocket. This concludes the initial phase of the bottle rocket project.